morning, students. In today's class, we shall discuss various properties of the inverse trigo functions. Properties of inverse trigonometric functions. So the properties are given in sets. So the first set has got properties like sine inverse sin x is x, cos inverse cos x is equal to x, tan inverse tan x is x, cot inverse cot x is also x, cosec inverse cosec x is x, and sec inverse sec x is x. The first set of properties has got 6 different results. The second set of properties is like this: sin inverse x is x, cos inverse x is x, tan inverse x is x, cot inverse x is x, cosec inverse x is x, and sec inverse x is x. Now looking at these two sets of properties, one thing is common. You notice that each result gives us x here. Likewise here, each result gives us x. But what is x? That's what we have to see. So when we are dealing with this kind of an identity, here x belongs to the principal branch of the sine inverse function. That means x is an angle. When we have this kind of an identity, so here x belongs to this closed interval. So now you can see the values of x's are different. In this case, x is one angle from the range of the inverse function. Here x is some value from the domain of the inverse function. Likewise here, we know here x should belong to the range of the function. Here also x is one of the angles of this open interval. Here x belongs to the open interval 0 to pi. In this case, x belongs to this closed interval except 0. And here x belongs to the principal branch of the sec inverse function. Here in this case, x belongs to the domain of the cos inverse function. Here x is any real number for the tan inverse cot inverse function, and here x has to be one of the numbers from this category. Right? Now the third set of properties, sine inverse 1 by x is cosec inverse x when x belongs to this subset of real numbers. Tan inverse 1 by x is cot inverse x when x is greater than 0, and cos inverse 1 by x is sec inverse x when x belongs to r minus 1 to 1. Now Now these results can be proved. So suppose we are proving this result here. So let us suppose that cos inverse x is theta, which means x is cot theta, or x is equal to 1 upon tan theta, which means tan theta is 1 upon x, which means theta is tan inverse 1 by x. So here if we substitute theta, we get the required result that cot inverse x is equal to tan inverse 1 by x. Now when we are writing these conditions here, that means the result is applicable only in that part of the real number system. So when we are using this result, the result is only possible when x is greater than 0. If x is less than 0, this result cannot be used. Okay. Likewise, when we are using the first result and the third result, we have to ensure that x belongs to one of these, x belongs to this category. Okay, so now moving on to the fourth set. See, sets have got different identities. We will be proving one of them. So in the next case, we have sine inverse minus x, which is minus sine inverse x. X belongs to this interval. Tan inverse minus x is minus tan inverse x. X belongs to R. So here we have cosec inverse minus x is minus cosec inverse x. So here x belongs to this interval. So out of these three, let's prove any one. So let us prove this one. So let tan inverse x be theta. That means x is tan theta. If we multiply both sides of the equation by -1, we obtain this. And we know from basic trigonometry that minus tan theta can be written as tan minus theta, and tan inverse minus x is minus theta. So in this last step, let us substitute theta. This is theta, so minus tan inverse x. So this is how the result is obtained. Here once again we have to remember that the result is applicable only in these given domains. So next set of properties, cos inverse minus x is pi minus cos inverse x, where x belongs to this closed interval. Cot inverse minus x is pi minus cot inverse x. X belongs to real numbers. And sec inverse minus x is pi minus sec inverse x, where x belongs to this interval. So now here one of these can be proved, and on the similar basis we can prove the other results. So let us prove, say, this result. Let us suppose cos inverse x is theta. So we get to know x is cos theta. Multiplying both sides of the equation by -1, we obtain this. And by basic trigonometry, we know the right hand side can be written as cos pi minus theta. Pi minus theta is the second quadrant. In the second quadrant, cos ratio is negative. So next step we can write down cos inverse minus x is pi minus. So here in this case, let us replace theta. Theta is cos inverse x. So this is how the result has been proved. On a similar basis, we can prove the other results. So next, set sin inverse x plus cos inverse x is pi by 2. So x should belong to the domain of the sin inverse cos inverse function. Tan inverse x plus cot inverse x is pi by 2. X is the set of all real numbers. Sec inverse x plus cosec inverse x is pi by 2, where x belongs to R minus this open interval. Let us prove this result here. So let us suppose that tan inverse x is theta, hence x is tan theta, and tan theta can also be written as cot pi by 2 minus theta. This is the first quadrant, and if you are writing the angle as pi by 2 minus theta, then you know the cot ratio will change to tan ratio. So here next step, cot inverse x is pi by 2 minus theta. So transposing theta to the left hand side, we get this. So in this step, replace theta. Theta is tan inverse x plus cot inverse x, which is equal to pi by 2. The seventh set of properties, tan inverse x plus tan inverse y is tan inverse x plus y upon 1 minus xy, where xy is less than 1. Next result, tan inverse x minus tan inverse y is equal to tan inverse x minus y upon 1 plus xy, where xy is greater than minus 1. Now when we are adding two tan inverse functions or subtracting two tan inverse functions, then these are the conditions which we need to check. The identity can be used only when these conditions are satisfied. So let us prove here, say the first result. Let us suppose that tan inverse x is A and tan inverse y is B, so that x can be written as tan A and y can be written as tan B. Since we have used substitutions A and B, let us add A and B and take tan ratio of these. So according to one result of trigonometry, this can be written as tan A plus tan B upon 1 minus tan A tan B. Tan A can be replaced by x and tan B can be replaced by y. So 1 minus xy. So in the next step, we can write down A plus B is tan inverse x plus y upon 1 minus xy. And then you can replace A and B, because we know A is tan inverse x, B is tan inverse y. So ultimately we'll get tan inverse x plus tan inverse y is tan inverse of this expression. All we have to remember is the result can be used only when xy is less than 1. Similarly, the other result can be proved on a similar basis, again remembering that this result can be used only when xy is greater than minus 1. So now one more set of identities which correlates the tan inverse function to sine inverse function. This way, where x belongs to this interval. The same result can also be equal to cos inverse 1 minus x square upon 1 plus x square when x belongs to this interval. 2 tan inverse x can also be written as tan inverse 2x upon 1 minus x square whenever x belongs to this open interval. So you can see this conversion formula can be used whenever we need a conversion from tan inverse to sine inverse or cos inverse or tan inverse to some other tan inverse form. So here we'll again prove one of these results. Let's prove the first one. So let us substitute tan inverse x as theta. So this means x is tan theta according to the first result. The left hand side 2 tan inverse x can be written as 2 theta. The right hand side we have sine inverse 2x. So what is x? Tan theta. 2 tan theta upon 1 plus tan square theta. Now here if you remember this result, you can write it down. In case you don't remember it, then simplify it further, converting tan into sine and cos. So if we convert it to sine and cos, we get this expression. Taking LCM and simplifying further, we get here this result. So in that case you can see that the denominator is 1, and the numerator can be written as sine 2 theta. So here we have done all these simplification steps. If we remember the result, then we know 2 tan theta upon 1 plus tan square theta can directly be written as sine 2 theta. Now this result will be equal to 2 theta only if this angle belongs to the principal branch. If you remember, the first set of properties we had written was sine inverse sine x will be equal to x only if x belongs to the principal branch of the sine inverse function. This is the first set of results. So here if we get 2 theta, then left side is equal to right side and the first result is proved. So how do we ensure that the result is 2 theta? Only when 2 theta belongs to the principal branch. So now how do we check that this angle belongs to the principal branch? So to check that, let us use this information. Now over there we are given that x belongs to this. We can write it down as x is greater than equal to minus 1 and less than equal to 1. So here we know we have taken x as tan theta. So replace tan theta is greater than equal to minus 1 less than equal to 1. Now here tan theta is an increasing function, so we can write down theta is greater than equal to tan inverse minus 1 less than equal to tan inverse 1. And since we know how to find out principal values, value is negative, so it has to be in the fourth quadrant, and in the fourth quadrant the angle is minus pi by 4. Value positive, so the angle is in the first quadrant and it is pi by 4. So this is true for angle theta. Our angle is 2 theta. So let us multiply each part by 2. The moment we multiply by 2, we get here minus pi by 2 and here we get pi by 2. So this tells us that the angle 2 theta belongs to the principal branch of the sine inverse function. Hence here we can write down 2 theta. So since left side is equal to the right hand side, the first result is proved. In a similar manner, in every set I have proved one of the results. So the remaining sets, in the remaining parts of the sets, we can prove in a similar manner. Now these are only those results which have been given in the NCERT textbook. There are numerous other results of inverse trigo functions given in many reference books. So we will confine ourselves to the results given in our own syllabus, and accordingly we'll use them to solve the questions.